Okay, let's jump right into this. It's an everyday action you've likely done this week, maybe even today. Just picture it. You're holding up your phone, kind of squinting, trying to scan this incredibly scratched, scuffed up QR code on a cafe menu. Or maybe you're wrestling with a battered shipping label on a delivery package that looks like it was, dragged behind a truck across 3 states. You feel that brief moment of frustration, point your phone, and boom, instant gratification. The website loads. But what actually happened in that tiny fraction of a second? How on earth did your phone make sense of that chaotic mess?
To understand how this works, we're going to completely slow down time for this explainer. We'll trace this incredible journey by looking at the exact 6-step chronological life cycle of a scan, from generation decisions to printing and physical damage, image capture, geometric detection, mathematical repair, and finally, the browser destination. We are following the data straight from the publisher's laptop right to your screen.
Now, there's a really common myth about how this whole process works. Most people just naturally assume your phone camera has some sort of magical software vision that intuitively sees right through the dirt, the coffee stains, and the physical damage on a package. You might think there's some AI guessing what the code says. But actually, that is simply not true. So here is the absolute crucial takeaway. Your scanner isn't magically reading through the damage. Not at all. It relies on a meticulously designed, highly robust 2-part defense system. First, the code is mechanically measured by your device to lock down its exact geometry. And then, it's mathematically reconstructed using a strictly finite repair budget to actually fix what's physically broken. Let's start at the very beginning with Step 1, generation decisions. Long before you ever scan anything, a human actor, maybe a warehouse manager setting up a supply chain or a marketing intern making a flyer, has to make some really specific architectural choices. They need to know what kind of data they're encoding, sure, but more importantly, they must determine exactly how much protective error correction to bake into those black and white squares. And by the way, in the industry, those little squares are called modules. Literally, every single module is a deliberate choice. The publisher basically chooses from 4 error correction levels. Level L gives you about a 7% data restoration rate, which is totally fine for a clean digital screen. Level M, sitting at 15%, is your standard for retail. But if you're printing for a gritty factory floor, you're probably going to jump up to level Q or even level H, which allows up to 30% of the data to be perfectly restored if it gets destroyed. Now, you might be wondering, well, why not just use level H all the time just to be safe? It's a delicate balancing act. Higher correction physically increases the code's complexity, forcing it to use hundreds of tiny, densely packed modules. If those modules get too small, your standard smartphone camera won't be able to read it from a normal distance. So it's a constant trade-off between resilience and real-world constraints. Which brings us to Step 2, printing and environmental damage. Once generated, that perfect digital code enters the physical world, which is basically an absolute gauntlet of potential destruction. Even before it gets outdoors, the printing process itself can cause catastrophic failures. Imagine a corrugated cardboard box flying down a sorting facility conveyor belt at like 15 miles per hour. The mechanical printer overhead has literally 1 microsecond to stamp that code. If there are heavy vibrations, or the printing distance is off, or the belt speed stutters, the printer instantly distorts the precise geometry required for scanning. And then, of course, comes the environmental damage. This is wild. Think about the stark difference between specific failure points. If a physical smudge or a sharp scratch hits the random static right in the middle of the code, the data area, it can often be completely mathematically repaired. But that exact same smudge placed over those large corner squares or over the invisible blank border around the code that we call the quiet zone, total scan failure, game over. That quiet zone is absolutely critical because it's the mandatory white space that tells the scanner where the background ends and the actual data begins. So structural damage to the corners or the quiet zone is fatal, but data damage in the middle, that's merely a flesh wound. All right, stepping into Section 3, phone camera image capture. This is the exact millisecond you finally point your device. Keep in mind, your device's optical sensor isn't actually reading a barcode yet. It's simply capturing light reflectance bouncing off dark and light areas. And this is a really fragile process. It's easily derailed by low-contrast colors, geometric distortion from curved packaging, or glossy glare from metallic foils. But here's a fascinating irony about color. Let's say a marketing team designs a gorgeous bright red QR code to match their brand. That red ink looks totally fine to your phone camera. But traditional retail scanners and warehouses use red laser illumination, When a red laser hits red ink, the ink reflects the light right back, washing out the contrast entirely. So a code that scans perfectly for a customer might be literally invisible to the global supply chain. Moving right along to step 4, detection and geometric sampling. Once the raw image is captured, your phone's software decoder kicks in, hitting the first of our 2 separate massive defenses: structural measurement. The algorithm immediately searches for the finder patterns, those 3 nested squares in the corners. What makes them an absolute marvel of engineering is their unique alternating ratio of dark to light. It is always exactly 1:1 to 3 to 1:1. Why is this pure genius? Because if you draw a straight line through that target from literally any angle, the scanner always reads dark, light, dark 3 times as wide, light, dark. Upside down, sideways, it doesn't matter. The ratio remains perfectly constant. That is exactly how the software orients the grid 360 degrees. Those squares have absolutely nothing to do with holding your website link. They are purely structural anchors. Next up, step 5. Mathematical repair and parsing. After the grid is structurally measured and oriented, we hit the second line of defense, where the heavy lifting happens. If modules were physically destroyed by a scratch on that box, the system utilizes the Reed-Solomon code. This isn't just basic software, guys. This is literal space-age mathematics, originally developed to combat communication noise for artificial satellites and planetary probes out in deep space. It works instantly inside your phone to repair your missing barcode data at the exact byte level. And it isn't just intelligently guessing the missing data either. By looking at the surviving pieces, it mathematically recalculates the missing information with absolute certainty. Think of this Reed-Solomon error correction as a strict, unyielding financial budget. Let's say our publisher chose a level Q code. That means exactly 25% of the total code words inside that square are permanently spent acting as a mathematical shield. But here is where it gets super interesting. If a company decides to stick a cute vanity logo right in the middle of their QR code for branding, that logo is technically read as damage by the scanner. It instantly eats up a massive chunk of this 25% repair budget before the code even leaves the printer, which of course leaves the code way more vulnerable to actual physical scratches out in the real world. Finally, we reach step 6, the browser destination. The structural grid was found, the math repaired the damage, and now the payload is ready. In mere milliseconds, the raw repaired bits are fully extracted and transformed back into 8-bit bytes, which are then translated into alphanumeric characters. At this stage, your mobile app looks at those characters and parses the URI syntax, essentially a set of digital routing instructions. It tells your phone exactly what to do: open Safari to show a menu, launch your banking app to make a payment, or trigger a map to track a delivery. And just like that, you've arrived. The true, undeniable genius of this entire infrastructure, which, by the way, was invented all the way back in 1994 by Denso Wave to track parts in automotive plants, is that it was designed with the explicit assumption that the physical world would try to destroy it. It relies on a beautiful paradox. It demands absolutely perfect geometry, but it backs it up with incredibly heavy mathematical shielding. So, the next time you scan a beat-up code on a shipping box or a coffee-stained table, just take a second to appreciate the incredible structural measurement and the budgeted mathematical repair happening right before your eyes in a fraction of a second. It really makes you wonder, if a simple black and white square is armed with satellite-grade mathematics just to survive a local coffee shop, what other invisible safety nets are secretly holding our digital world together? Thanks for checking out this explainer, and we'll see you next time.